Welcome to this short video on optimization. To optimize something is either to maximize it or to minimize it. With that in mind, read this problem to yourself. So this is an optimization problem because we're trying to find the minimum amount of fence that we can use to build the specified project. So when you're trying to optimize something, one of the best ways to do it is to create a formula based on various choices or variables that you have in the situation. For example, we're going to create our optimization equation here using the variables C and W. C and W are lengths that not only do we not know, but can actually vary from different ways of building this rectangular patch. Let me say that a different way. If we have to build a patch whose area is 216 square meters, as indicated by the directions, there's infinitely many ways that we can do that. In other words, there are infinitely many rectangles whose area is 216. So among these infinitely many choices, how are we going to find the best way in terms of using the minimum amount of fence that we could get away with? Well, for that we'll need an optimization equation, and I like to start with typically with an equation that has two variables, and we'll use W and C as those variables here. It doesn't matter what we call them, those are just random letters I picked. So the amount of fence that we'll need can be represented by 3 times C, because there are 3 fence segments of length C, plus 2 times W, because there are 2 fence segments of length W. We call this the optimization equation because it's the equation for the quantity that we're trying to optimize. You'll notice that we are trying to optimize, or in this case, minimize the amount of fence needed. So my optimization equation should express the amount of fence needed in terms of the variables of the problem. But there are too many options here of what C and W could be for us to effectively run through all the possible choices. It would certainly be possible to pick values of C and W that would give a value of 216 square meters as the area, and then compute the amount of fence for each one. But this could be a very cumbersome process. So what I'd like to do to simplify the process is change my optimization equation from 2 variables into 1 variable. In order to do that, I'm going to have to either eliminate the C or eliminate the W. If I can eliminate one of these variables, then it'll be more clear what option I should pick to optimize or minimize the amount of fence. But the only way to get this equation into 1 variable is to use our constraint that we have an area of 216 square meters. I'm going to make a constraint equation here, and that will allow me to change my optimization equation on the left from 2 variables into 1. Now back to the diagram in the upper right corner. There are infinitely many choices for C and W that would allow for an area of 216 square meters. But among all those choices, it must be true in all of them that whatever I choose for C times whatever I choose for W has to be 216 square meters. If that's to be the area of the enclosure, then that equation must be true. Now notice this is not the optimization equation. We're not trying to optimize area. Area is what it is. It's 216 and I can't change that. So I build a constraint equation out of the fact that I can't change, or the fact that constrains the construction of the project. So regardless of my choice of C and W, it must be true that C times W is 216. Now how can I use that constraint equation to change my optimization equation from 2 variables into 1? Well, I could solve the constraint equation for either variable. And it really wouldn't matter which one here. Because it doesn't matter, I opted to solve for W. Now, this does not give us a numerical answer for W, because there are, in fact, infinitely many things W could be. But it gives a relationship between W and C. Solve for W. Now what I can do is plug that into my optimization equation. Plugging that in gives me the following algebra result. I chose to simplify that, although it's not really necessary in this particular problem, but I chose to just for my own purposes. What does this mean? What it means is I have the amount of fence I would need as a function of C. Now, how could I then choose a value of C that would make F as small as possible? In other words, what value of C would give me the minimum amount of fence needed? Well, one thing you could do, and I don't recommend this, but this will give you a perspective on the problem. One thing you could do is you could look at this diagram. What I've done here is I've plugged in many different values for C into this equation. And the second column, or the F column, tells me how much fence I would need to build this entire project for each of those choices of C. And it would appear that 72 meters of fence is the lowest that F can get based on all these particular choices of C. But I don't really consider this a valid solution to the problem, and if it does end up being right, it would only be by accident, because we have no reason to assume that C would be a whole number, and even if we did, it wouldn't necessarily be on this list. But this does give us an early indication that if C were 12, then I could get away with 72 feet of fence, and that does appear to be the minimum anyways, but we don't know that for sure. So rather than making a table and picking specific values for C, how is it that we can consider all the values of C at the same time? To do that, we need to graph this function rather than make a table out of it. Because a graph effectively shows infinitely many points, and therefore infinitely many values for C and the corresponding fence values. So what I'm going to do now is I'm going to graph F as a function of C. And this is what I got. Now to do this, you can use almost any app these days will graph one function of a variable. What I did is I went to Desmos and I graphed this. And rather than using F and C, that particular app uses Y and X, as do most. So you have to keep track in your own mind of what Y represents and what X represents. But that's how I came up with this graph. Now, apps vary, but some apps will find the minimum for you. Desmos is one of those apps. Isn't it true that the lowest point on this graph represents the least amount of fence? So I had Desmos find the lowest point on this graph for me. It was actually quite easy, and you can figure that out very simply on your own. And it did in fact turn out to be the point 1272, as we thought it might be, based on the table, although we didn't have the proper evidence at the time. You see, the table was only computing maybe 8 or 9 values of C. The graph computes theoretically infinitely many values, but in the case of an app, thousands of different values of C. So when Desmos told me that 12,72 was the minimum of this function, it was basing that on what I can only assume would be tens or hundreds of thousands of different calculations it did in a microsecond. So I now know the minimum of this function, And what I have to do next is interpret what that means. What does that mean about the actual building here? Well, clearly it's the minimum of the fence function, so it in some sense represents the minimum amount of fence that I can get away with. Let's not forget what our x and y variables, our x and y axes, represent in this particular case. Because we're graphing f as a function of c, f is the y-axis, and c is the x-axis. And keeping in mind that 12, 72 is x, y, I can now interpret this optimum point, or minimum point in this case, as if c is 12 meters, the amount of fence needed for the whole project will be 72 meters. And furthermore, because that's the lowest point on the graph, I can assume that any choice other than c equals 12 will lead to a higher amount of fence and hence not be optimum. Now, one thing we haven't figured out yet in the building process is what W has to be. But that's easy enough to do. You can simply plug in 12 for C now that we know that that optimizes or minimizes our fence. And plugging in 12 for C tells me that W is 16. And now I have a full interpretation of the optimum point. That we need at least 72 feet of fence to build this. And with that, you will make a 12 by 16 rectangle as your enclosure. And that completes this lesson.